discuss a little bit of an in-depth subject, which is how the VFD actually manipulates current in the AC induction motor to produce torque. First and foremost, we want to understand that current is torque in the AC induction motor. And by the way, as we're discussing the AC induction motor, the vast majority of what we're talking about, with the notable exception of the concept of slip, is going to be applicable to AC permanent magnet motors. You want to understand that the basic 6-transistor bridge of the output of a VFD, the inverter section, the section that converts DC back to AC, is the exact same power deck design used in a servo amplifier. A servo amplifier is nothing more than a VFD with a much faster processor, sort of different firmware associated with it, higher feedback, of course, feedback being the encoder on the motor. In most cases, servo amplifiers are closed loop, 99.9%. But a servo amplifier is nothing more than a VFD on steroids. The basic manipulation of current in the windings of the servo motor, the 3-phase alternating current windings of the servo motor, are the same as in the induction motor. The difference between the two motors, of course, is the rotor. The servo motor has a permanent magnet rotor, typically magnets on the surface of the rotor itself. The induction motor, the field is induced from the stator. So, as I'm stalling, waiting for you, Scout, to download this, I'm going to talk a little bit about the fact that what we do today is very similar in principle to what we did when we first introduced the transistorized drive back in 1983. We still, with the exception of matrix technology, which we're not talking about today, we still only have the ability to switch from a fixed DC bus. So if you'll remember some of my other presentations, the front end of the inverter is a diode bridge, and it rectifies the incoming AC, typically 3-phase, and let's keep our discussion at 460 volts today, 460 volts, 440 volts, 480 volts, it's all pretty much the same thing. And we rectify that to whatever the AC voltage is times the square root of 2, because that gives you the peak of the sine wave. A bridge rectifier, 6 diodes. We have DC of a magnitude of about 680 volts rail to rail. Now, let me share the screen here. So I hope you can all see that. Can't pipe up, but in review, this is what we're talking about. The 6-transistor inverter section. Here is the full wave bridge rectifier taking the AC, making DC. This is the positive rail here. This is the negative rail. And between these two rails, you have 680 odd volts DC in the unloaded state. Of course, as you run the motor, and the motor draws power through the transistors off of the DC bus, that DC bus is going to rise and fall accordingly. But the static condition, the nominal condition, is input voltage times the square root of 2. Now, this 6-transistor diode bridge here, you see there's a transistor and a diode in sort of anti-parallel. Transistor obviously pointing down, the diode pointing up. The diodes are there to take the AC from the motor during a regenerative portion of your application and rectify it and put it back on the DC bus. The transistors are to manipulate the DC and create the current flow in the AC motor that we want, the sine wave. This is a digital simulation of an analog function, and we want to create a perfect sine wave of current in the motor. The voltage doesn't look sinusoidal. Now, when the motor is connected directly across the line, of course, you have a sinusoidal voltage, and then you get a sinusoidal current. With the drive, we can't do that. We're going to, because I can only switch off of a DC bus of constant voltage, I can only use pulses of voltage through these transistors, which are basically just really fast light switches. There's no amplitude modification here whatsoever. So when I close this transistor and that transistor, and I energize the winding between T1 and T2, I can put a pulse of DC onto that winding. How do I get sinusoidal current from that? And that's the big question today. So if I go up here, let me show you how that's done. Nominally, I'm going to vary the pulse width to get this target sine wave. This is current over time in this particular little diagram here. Please ignore the rest of it because this is drawn from another presentation. So I'm going to pulse with narrow pulses, turn on, turn off, because that's all I can do. I just have a transistor. So I turn on, turn off, then I have a certain delay or off time, and then I turn the next pulse on. But what is behind this pulse width modulation? We've all seen this, but it certainly doesn't result immediately in this perfect sine wave as an output. So this is what I want to dive into today. Let me see if I can find that diagram. Here we go. So, scope signals. And here is our pulse width modulation. Bear in mind that we don't pulse this slow. The slowest we pulse is 2,000 times a second. And if we're running at 60 hertz, then it's 2,000 divided by 60 for the number of pulses per sine wave. But for illustrative purposes, here's what happens. We start here in the lower left-hand corner, and we turn on the transistor and apply full DC across the target winding. What happens in the winding is that the current starts to rise, but at a different rate than the voltage pulse. And this is the key. That voltage pulse goes up pretty much straight. We want it to. We don't want to be in the switching phase longer than we have to be, because that heats up the transistor. When the transistor's at zero, or when the transistor's gated full on, it has the minimum number of losses, but it has the maximum number of losses during these switching transitions. Now, they're not perfectly straight. We don't instantly turn on the transistor. And in fact, we have in later years had to turn the transistors on much slower than we used to, because every time we turn on the transistor, there's this voltage spike that can go to 2 to 3 times the actual value of the DC we're switching. So in order to reduce that voltage spike, we've had to start to ramp the transistors up. Now, there's various techniques in circuitry to do so, but it basically means that we're in transition on the transistor junction longer, therefore more heat, so we've had to use bigger transistors. The reason we've been motivated to do that as VFD designers is that that high pulse at the leading edge of the voltage pulse, the high spike, sorry, is very damaging to the motor winding. It causes common mode noise that creates voltage on the rotor that comes back through the bearings and arcs the bearing races. lot of bad stuff. So we want to keep that spike down. And NEMA MG1 part 3132 tells us that we may not spike over 1400 volts, which meant we had to slow down the transistor rise time, which meant we had to use bigger transistors. So, however, let's go back to our original discussion. Let's switch on the transistor. And why do we not get immediately a same shape in the current waveform? If this was a resistive circuit only, we would. But because the motor is the largest component of impedance in the rotor of the, or in the stator of the motor, because the stator is copper wound around iron, is its inductive reactance. Inductive reactance acts as a shock absorber to changes in current. And we depend upon that to shape the waveform we're trying to shape in the motor, the current waveform. So when I switch on, I get this rise time. And the target waveform is red, as you can see. The acceptable bandwidth is green. The deviation of the blue waveform from the red waveform is my harmonic distortion in simulating this analog function. With those things defined, I turn on, I get a certain rise time in the current. When I get to the top level, I switch the transistor off. The current starts to collapse. Again, not precipitously, but at a certain ramp down. Again, the inductive reactance that we're playing with. When I get to the lower limit, I switch the next pulse on. And the next pulse happens to be on for longer because it takes longer for me to climb up to the next limit that I see. Any questions on this? This is actually the core thing that I wanted to teach today. I was hoping to give you some AC induction motor basics, and I may still do that today if this thing downloads from Yaskawa fast enough. Let's see where we're at. We're at 1.5 gig, and I got to go to 4, so we may not get it in today. So, any questions on that? This is wave shaping using the inductive reactance of the copper winding of the motor and timing on the pulses of the transistor. Because we only have a full voltage DC bus to switch from, and we can only manipulate on time and off time. We cannot manipulate amplitude. We can only manipulate width. PWM, pulse width modulation, PAM, pulse amplitude modulation. As a side note, the matrix drive has pulse amplitude modulation and pulse width modulation. One of the reasons why, amongst others, matrix drive can produce a perfect sine wave on its output without filters. In the case of the standard drive, which we still sell 95% of the time today, no, not so much. They're still limited. So Yaskawa finally popped up. All right, hang on a second. I am going to play this video since it came in time, and then we could go back to this particular discussion and review it. This is one of the excellent Yaskawa e-learning modules. It happens to be focused on motor basics. I'm going to cut it short and push it because it's 28 minutes and I don't have that time. But we're going to get to play the relevant parts of it. So Yaskawa's e-learning module on AC induction motors.
Here, since there's supposed to be volume
Uh-oh. Yes, there is. Hang on. I know why that's the case. Thank you for piping up. I there is I don't know why Teams does this, but when you share content, they don't make sound the default. And I always, because I'm an idiot, I always forget to turn on the sound. So now you should hear this. Hang on.
Some questions to review the
Can you hear that?
Covered. Oh, one note before we start. In many applications,
Yes.
the speed of a three-phase induction
Yes.
motor is often controlled by a variable frequency drive. Information we present today will give you a good understanding of three-phase induction motors and prepare you for the next video in our series titled Variable Frequency Drive Basics. Let's get started.
We won't get to that VFD basics video today, but you can download it from your Scowl, hopefully at a faster bandwidth than I have.
Let's start by identifying the components of a typical three-phase squirrel cage type induction motor. Inside the stator frame of the motor are the stator and the stator windings. The stator is made up of a series of stacked, insulated, and compressed iron slices with cutouts or slots through which we run the stator windings.
Stator being stationary, rotor being rotating.
We use stacked metal slices to reduce electrical losses in the system. Centrally located within the system. The rotor is basically a cylinder with an iron core. It's also made of laminated slices, just like this.
In a permanent magnet servo motor, you would have a rotor shape, but all this magnetic steel is replaced by magnets that are glued to the surface of the rotor. And the reason they call it permanent magnet is that the magnets generate the magnetic field all the time. In an induction motor, as you will see, there's no magnetic field on this rotor. You need two magnetic fields to run any motor. One magnet pushes or pulls the other magnet. The electromagnet generated by this stator is the first magnet. The reason we call it an induction motor is that we induce a current in these circuits in the rotor, and once you have current flow in the rotor creates its own magnetic field, and thus your second magnet field.
The rotor has conducting end caps on each end and conducting bars running through the slots in the laminated slices that connect to the end caps. The result is a rotating cage that looks similar to a squirrel cage. That's why induction motors are commonly referred to as a squirrel cage motor. The rotor is attached to the motor shaft. Bearings support the motor shaft, allowing the shaft and rotor to rotate as it remains centrally positioned within the center enclosure. The shaft transports the mechanical energy created from the rotor to the load. And an air gap between the stator and rotor eliminates any contact between the two components. Protecting the components is the enclosure, which consists of the motor frame and the end bells. The end bells contain bearings, which allow the rotor shaft to turn freely on its axis. Now, the type of enclosure can vary depending on the motor's application. We'll talk more about the different types of enclosures later. All right, before moving on, here's what are the two major components? How these two components create electromagnetic induction?
Here's when you muted yourself, I think the audio went away.
Pierce, I had muted you because you had a lot of background noise.
Oh. Okay. I don't know what I'm just sitting in my chair, but okay, let's go. So you can't mute me then, I guess, because um, otherwise I lose the audio, right?
Yeah, I didn't realize that would happen. I would have done it.
By moving it through a magnetic field, or by having the magnetic field move or change around a stationary conductor. In a three-phase induction motor, the
I want to
stator
repeat that
and
because
how these two
that is
components
really
interact with
important.
each other to create electromagnetic induction. We'll start with a definition. So, what is electromagnetic induction? Electromagnetic induction is a process in which current is created in a conductor by moving it through a magnetic field, or by having the magnetic field move or change around a stationary conductor. In a three-phase induction motor, the stator produces the varying, or to be more exact, rotating magnetic field needed to initiate and maintain the induction process. And let's look at how that's accomplished. As we described earlier, the stator has a core of individual laminated plates that are laminated together. These plates have slots in them, which allow insulated electrical windings to pass through the core. The stator windings are distributed around the stator in such a way that when current flows through them, the stator produces a magnetic field. To better understand how the magnetic field is produced, think about the electromagnetic demonstration you may have seen back in science class. An insulated copper wire is wrapped around a nail. When voltage is applied across the wire, current flows through it, and the nail becomes an electromagnet. In this case, you can think of the nail as the stator's core and the copper wire as the windings. Certain metals, such as iron, like this nail, have magnetic properties where the atoms are randomly oriented. This random scattering of atoms cancels any natural magnetic field. But when current is passed through the coil of wire, it produces a magnetic field which forces the atoms to align in the nail. These aligned atoms combine to produce a strong magnetic field from the nail. And the same is true of the stator's core. Three-phase induction motors use balanced three-phase power. The phases are electrically separated from each other by 120 degrees. When you apply alternating current, or AC, the flow of electrons reverses direction halfway through the cycle. To understand how quickly this happens, remember that the standard AC power frequency in North America is 60 Hertz. And that means that current flowing through the stator repeats one electrical cycle every 16.6 milliseconds. And that's faster than the blink of an eye. Here's an example of a simplified model. You can see that the stator is mechanically stationary, but when we combine three-phase alternating current with the correct placement of the stator slots, we create a rotating magnetic field. Now, let's look at the rotor and see what role it plays in the induction process. The rotor, iron core, conducting bars, and conducting end caps are constructed to conduct electromagnetic current. As the stator's magnetic field rotates, it induces current on the bars of the rotor. As the rotor bars are shorted at both ends using end rings, there is now a closed path for the flow of current in the rotor bars. This, in turn, aligns the atoms in the iron cores of the rotor to produce its own magnetic field, which opposes the magnetic field produced by the stator. This happens because any induced electromotive force always produces current that opposes the stator's magnetic field. So, the rotor's magnetic field opposes the stator field, which causes it to repel from like poles and attract to opposite poles. This causes constant shifts as the rotor is attracted and repelled by the rotating magnetic field. We've covered the stator and the rotor, and we have seen how each has their individual function in the induction process. But for induction to take place, there's a third element needed, and that's relative motion. Generally speaking, relative motion is a calculation between the speed of one moving object relative to the speed of another moving object. In this case, the relative motion between the rotating magnetic field of the stator and the rotating rotor. As you can see, the rotor rotates slower than the stator. How much slower depends on the motor's external load and how much energy is lost internally from friction, induction leakage, and other causes. Now, here's another question. Is the rotor connected to the three-phase incoming current? The answer is no. The stator creates a rotating magnetic field, which induces a voltage in the rotor bars, which are shorted on the motor. That allows current to flow in the rotor, which then creates its own opposing magnetic field to the stator field. The difference between the speed of the magnetic field and the speed of the rotor is called slip. To help you understand, let's take a moment to define some terms that we'll need to know as we move on. The speed of the rotating magnetic field in the stator is called synchronous. We can calculate synchronous.
Synchronous means the same. And I just want to note here that in Europe, the synchronous motor is their word for the permanent magnet motor, because there's no slip in that type of motor. In the induction motor, where you'll see there is slip, in Europe they call that an asynchronous motor, or not the same.
Or sync speed by using the formula 120 times F over P, where F is the frequency of the AC power supplied and P is the number of motor poles. We'll talk about motor poles in a second. So, with some simple math, you can see that a 4-pole motor connected to a 60 Hertz power source would have a sync speed of 1800 RPM. The mechanical speed of the rotor is called the rated speed. A rated speed is based off a motor's rated load. You can usually find the value for the rated speed on the motor's nameplate, indicating the general speed of the rotor at a rated load. Using our previous example of a 4-pole motor running on a 60 Hertz supply, the rated speed would normally be between 1725 and 1750 RPM. So, as you can see, with AC induction motors, the rotor always rotates slower than the magnetic field of the stator. The difference between the sync speed of the stator's rotating magnetic field and the mechanical speed of the rotor is called slip. The amount of slip depends on the amount of the motor's load. The greater the load on the motor, the slower the rotor turns in relationship to the stator's rotating magnetic field. The more this difference increases, the more slip increases. To illustrate slip, pay attention to what happens to the speed of the motor as the load is increased and decreased. You can see that as the motor load increases, the mechanical speed of the motor decreases. And as the load is decreased, the speed increases. This increase and decrease in motor speed together is called slip. Well, let's take a moment to review. Now, here's another question. Is the rotor's speed the same as the stator's rotating magnetic field? The rotor's speed is always slower than the rotating magnetic field in a positive direction. If both were traveling at the same speed, there would be no induction, and the rotor would not be able to create a magnetic field. Induction motors handle various loads and various speeds. One way is to change the number of poles in the stator. You can increase or decrease torque by adding or subtracting the number of poles. The more poles there are, the slower the magnetic field rotates. Using the sync speed formula, we can calculate the magnetic times 120 divided by the number of poles. So, say you have a 2-pole motor powered at 60 times 120 equals 7,200. 7,200 divided by the number of poles, in this case 2, shows us that the numbers are evolution of motor. But what happens to the motor's synchronous speed if we add more poles? If, like the example just mentioned, the motor is powered at 60 Hz and we have 6 poles instead of 2, the synchronous speed produced by the stator decreases to 1200. You can see by this table that sync speed decreases as you increase the number of poles. So, high torque induction motors have slower sync speeds and lower torque motors of the same size have less torque and higher synchronous speeds. One thing to note, as pole count increases, so does the cost of manufacturing. So most induction motors are 2 or 4 pole configurations. If more torque is needed, most people will opt for a larger motor instead of using a single. Well, it's time for yet another. If we have a motor with a rated speed of 1770 RPM, how many poles? And the answer is 4 poles. We know that our rated speed is going to be a little bit less than our sync speed. Looking at this table from earlier, we see that a 4-pole motor has a sync speed of 1800 RPM. This tells us that if we include slip, we are around 1774 RPM. In this next session, we'll discuss speed, torque, and what they mean. Induction motors are used to produce torque or to complete. As they work, induction motors use electrical energy to produce the torque needed to accomplish that task. A speed shows you how the torque produced by an induction motor varies throughout the different phases. Starting torque is the amount of torque an induction motor ramps up from a standstill. Looking at this example of a starting torque, you can expect the starting torque to be about 150% of rated torque. Pull-up torque is the amount of motor torque available as the motor accelerates toward its rated speed. If the motor's pull-up torque is less than the amount required to accelerate the load, the motor will never reach its rated speed. As the motor continues to accelerate toward its rated speed, it encounters its breakdown torque. Breakdown torque is the greatest amount of torque a motor can generate. When the motor has accelerated itself to its rated speeds, the motor should be producing between 80 to 100% of its rated torque. That is, of course, if the machine has been designed properly. Now, let's look at our example again, but this time pay close attention to the motor torque. As the load is increased and the motor's speed increases, the amount of torque produced by the motor increases. Watch it follow this line. You can see that torque and current are proportional. That means an induction motor draws more current. So, as the load increases, it increases the amount of current that the motor draws, and consequently the amount of motor torque produced. Okay, let's look at another example. Let's say the machine load is very large, so large that it causes the motor to produce torque near the motor's breakdown torque rating, and then beyond it. You can see as the load increases, the amount of torque increases and follows the speed. Because of this, the speed of the motor begins to decrease and the amount of current flowing to the motor increases. Current flow in the rotor begins to increase as the rotor becomes saturated. The current in the system as a whole is going to increase. When the motor slips beyond its breakdown torque, it begins to produce less torque, which then causes the motor speed to decrease even more, and in many cases, slow. This situation usually results in damage to the motor if left in this state due to overheating of the stator. Though typically there's an overload relay that will protect the motor from damage. Well, here comes another quiz question. If we look at the speed, at what point is the torque at its maximum? Did you come up with breakdown torque? I hope you did, as breakdown torque is the greatest amount of torque a motor can generate.
And here I want to pause and have you refer to this diagram here. This represents the motor speed torque curve at 60 hertz. Obviously, with a VFD, we will never let the current rise to the point where the motor stalls. The VFD will take action, either fault tripping or, if the VFD is programmed as such, reducing the speed, folding back the output frequency to reduce the current. However, what's really important to understand here in terms of the AC induction motor with reference to the VFD is that this portion of the curve is completely irrelevant to VFD operation. And the reason is this. This is the 60 hertz curve, okay? Speed, as you know, is proportional to frequency, and this is 60 hertz. If I go to half speed, then either I'm going to go here to 30 hertz. What happens to this waveform? It actually moves to the left. As you raise and lower the frequency to the motor, this whole curve shifts. So if I'm at 30 hertz, I can redefine this and make this point 30 hertz because that's the sync speed now. With VFDs, 60 hertz is no longer an important point. It's no more important than anywhere else on the frequency range. So this is now 30 hertz at half speed. But what's really cool is that when you get down to, say, let's just to keep the math simple because we actually go down to 0 hertz. But when we're at 3 hertz, this is now the sync speed at 3 hertz. So you still have this same curve here. You want this curve, by the way, to be as flat as possible with as little slip reduction as possible, because that is ideal for an AC induction motor. When you optimize this section of the curve, you actually deteriorate this section of the curve. It's sort of a rob Peter to pay Paul situation, but in this case we don't care because this section here in an AC induction motor's speed torque curve is irrelevant to the VFD, because as we move down in speed, this section of the curve is the only relevant portion of the curve. We're always operating here. The VFD allows us to stay here, never getting into this zone. So the important point to take away from this interruption is that this wave shape, this sync speed, applies to the output frequency, not just 60 hertz. When you're running at half speed, 30 hertz. When you're running at a 10th speed, you're running at 3 hertz. And let's take the example of 0 speed. If we're running at, if this is 0 speed, we're still going to have torque, but the motor's going to be going ever so slightly in reverse, about minus 24 RPM. But here's the punchline. If I want to control 0 speed on the motor, let's say I want full torque at 0 speed. In other words, float the load on a hoist. I will make this 0 speed. This will be whatever positive frequency output is necessary to make this 0, the corresponding frequency to the motor's slip RPM. In the case of a 1775 RPM motor, 4-pole, it's going to be, a couple of hertz, 1.5 hertz. So I'm going to run the motor, the motor's synchronous field at, say, a hertz. That gives me 0 speed on the rotor, but it gives me full torque. That's how we accomplish full torque at 0 speed. And that is a capability that most drives have today. Albeit most drives require an encoder to do so that we can accurately track this rated speed and manipulate this sync speed so that we don't get too much oscillation in the output. Yaskawa has technology to do this open loop, where we don't need an encoder and we can still maintain the motor at 0 speed, full torque.
Is
Not
that
as
through
precise control.
tuning? Pierce, is that through? It used to be that you would go in and you would start the motor in a tune, so the drive actually maps the motor, and then it can give you zero. Is that what they still do? But you don't have to program it to do that now, right?
Yeah, it's auto tuning. In the case where you want,
Yeah.
Where you want to operate precisely at 0 speed, full torque, open loop, yeah, you're going to have to auto tune the motor or manually enter in accurate motor constants into, in Yaskawa's case, the E2 parameters.
Mm-hmm.
Yes, that's a very good point. However, the other thing that you can do, and the Black Max motor and other inverter duty motors that are manufactured, a lot of European motors are made with very, very flat speed torque curves in this region. They're very low slip. You heard the presenter say that it's, normal rated speed is 1775, 1750. In the case of NEMA Design B motors, the slip is 3 to 5%, so, like 1750, 1740. In the case of these dedicated inverter duty motors, their slip can be as little as 15 RPM. They're almost permanent magnet-like, which is the whole point, because you're now getting into induction servo type of performance. With that flat speed torque curve here, you have less variation in RPM, less sensitivity to load in RPM, makes it easier to keep yourself at the rated speed you desire. In the case we're talking about here, 0. But even if you want 50 RPM rated speed, with a flat speed torque curve here of one of the inverter duty motors, low slip inverter duty motors, your control is very much easier as your load varies. I hope you understand that. Obviously, putting an encoder on there, we know what the rated speed is, and therefore we can have this kind of performance quite easily because we have instantaneous feedback from the encoder. But in the case of open loop, we don't have that, and therefore the flat speed torque curve is that much more important. So, thank you for allowing me to interrupt.
Now let's discuss the NEMA design types and why they are important. An organization called the National Electrical Manufacturers Association, or NEMA, establishes technical standards for the manufacturing of electronic products. NEMA has established standards for 4 different designs of electrical induction motors, which are A, B, C, and D, respectively.
I'm going to jump on this section here because we're running out of time. A is the design that I'm talking about for these very flat speed torque curves. You can see that. You can see that the slip at 100% is much lower than design B. Design C and design D, we don't even play with those designs. These are old designs that were used in across-the-line contactor-based applications. Design D, for example, is a torque motor. You can see that it never stalls. It never has this break point where it just drops to 0. It's like a giant spring. And design D motors were used in crane and hoist applications back in the old days when the only thing we had was a contactor. Today, the only 2 relevant designs that we want to talk about are design B and design A. Design B is your garden variety AC induction motor. With an encoder, I can make it do pretty much anything a design A motor can do. It has slightly less of a torque range, but as long as I program my drive never to go beyond this point, the difference between A and B is irrelevant. The A motor, if you can buy it, it typically is about 15% more cost than a design B motor, and it's not as off the shelf as the design B motor, but it certainly is a better performer in terms of a VFD. The other thing that a design A motor has is a slightly better torque to current ratio. It's more efficient, and as a result, you get a bit more torque for your money. The main reason I would use the design A is if I was not using an encoder and I wanted to have good velocity control. Now, at this point, I'm going to introduce a concept to you that is very important. There are three loops of control when we are talking about motor control. The inner loop, the most basic loop, is the current control loop. If I can control current, which I can with the VFD, again, back to the pulse modulation technique that I was showing you earlier before I started this motor presentation. If I can control current in the motor, I can control torque. Once I can control torque, I can then control speed of the motor. And for higher order applications, once I can control speed or velocity in the motor, I can then control the position of what I'm driving with the motor. Now that third loop, the position loop, the outer loop, is typically only relevant in positioning applications which we would normally do with servos. And as I'm hoping you're beginning to understand, we can do with the concept of induction servos. There should be in your mind at the end of this presentation a seamless transfer between servos and induction motors in positioning applications. The transition point is this. It's dynamic response. How fast do you need to get from point A to point B? How fast do you need to settle once you arrive at that destination? Servos are very good at that. The main reason is that they have much lower rotor inertias. So when you are decelerating, you're decelerating a much smaller mass. A servo motor at 1 horsepower is smaller than an induction motor at 1 horsepower. Its rotor is smaller. Also, servo amplifiers have much faster current loop control speeds. The current loop in a servo, in most cases, is around 62 microseconds. So you're making a decision and correcting on the current loop that fast, which means you can therefore make decisions on the velocity loop, the next loop outside the control loop or the current loop, much faster. And then, of course, again, it applies to the position loop. So if you're at 62 microseconds on the current loop, you may be at 125 microseconds on your velocity loop, and maybe 300 microseconds on your position loop. How fast do we do things in an inverter, a VFD? Well, the VFD, instead of being in the microseconds, our control loops are in milliseconds. And therefore, they're much slower to respond. So the transition point between using a full-on servo and, say, an induction servo with an encoder feedback is dynamic response of the application. If the application is such that you don't really need the dynamic response, you should consider induction servo from the standpoint of cost. Capability-wise, theory of controlling current, velocity, and position in a closed-loop AC induction VFD combination, an induction servo, is the same as in a normal servo. The only difference is the dynamic response or response rate. So in that case, we would use a design A motor and an encoder to optimize our induction motor reactivity, but we're always going to be slower than a servo. And in many applications, that doesn't matter. The applications where it doesn't matter is when the mechanical constant of what we're driving is so large that even with a fast servo, we can't affect it anyway. Something like a gigantic flywheel or something with a big metal mass driven at a big, large reflected inertia. In those cases, you don't need the dynamic response of a servo, and therefore you're just wasting money. In fact, in many cases, the servo inertia mismatch on those applications is actually going to be a disadvantage. So, onward.
Standardized design has unique speed, torque, and slip capabilities depending on the work they perform. For a
I'm going to jump ahead here.
application. answer, Design A and Design B are both suitable for this application due to their low amount of slip and high breakdown torque.
This we're going to skip over also.
Motor poles indicate type, either A of overloading as ENCL, and the final type is a totally enclosed blower-cooled or
This is important.
BC as ENCL. An open drip-proof or ODP enclosure is typically used for indoor applications. The open drip-proof enclosure allows outside air to circulate over the windings while preventing any liquid from entering the enclosure within 15 degrees from vertical. A totally enclosed, non-ventilated, or TENV enclosure uses cooling fins to dissipate heat instead of a fan or vent opening. They're designed for installation indoor or outdoor in dirty and or slightly damp conditions.
Thus you see the Marathon Black Max, which is the classic inverter duty motor in the United States. There's lots of people that make them. Marathon's just better at advertising them. TENV. What do you think? The next one he's going to talk about is TEFC, where the motor depends on a fan on the shaft of the rotor to cool itself. As you slow the motor down, how effective is that fan to cool the motor? The CFM will drop off as the square of the speed. So at half speed, you get a quarter of the cubic feet per minute of air. In a constant torque application, that doesn't cut it. Because if you're constant torque, constant current, you're constant losses. And therefore, you need full CFM. TENV is one way to get it because it's designed not to depend on a fan. You'll be able to get TENV designs 30 horse and below, typically more commonly 20 horse and below. And these motors will run hot. They'll run around 135 C, which is well within the rating of the Class H insulation that they're manufactured with, which is 165 C. But you know, they'll seem hot to the touch. Well, that's not that. They're still running within their design limits. TENV is what you want to use for constant torque variable speed applications, because if you rely on a fan that's driven by the rotor shaft, the motor will overheat.
A totally enclosed fan-cooled, or TEFC enclosure, is cooled by a motor shaft connected to an exterior fan. Though they're not waterproof, TEFC enclosures are used outdoors in dirty locations. And the final type is a totally enclosed blower-cooled, or TEBC enclosure, which is cooled through forced convection by a rear-mounted blower. You'll find
This type of motor is what you would use above the 20 to 30 horsepower range where TENV becomes unavailable. It's just too hard to cool the larger motors ambiently. There's not enough surface area on them. So what we do is we put a constant speed blower on the tail end of the motor so the fan runs at a constant speed regardless of the rotor speed of this motor controlled by the VFD. And that is the TEBC motor, which is, again, an AC induction type motor. Now, you'll probably play hell getting an encoder with a blower on it. There are companies that manufacture that. We at Western Automation, we don't represent a lot in the AC induction motor, but we can help you access those motors. What's even more complicated is, you know, you're doing an incline conveyor or a hoist or a winch or something like that, and you want to brake. Well, now you got a blower, you got a brake, you got an encoder, and you have the induction motor itself. Now, with servos, most servos come with a holding brake and an encoder integral to the motor. It's very easy to spec a servo brake motor versus a servo motor in the manufacturer's catalogs. I don't see a lot of blower-cooled servo motors, to be honest with you. We're talking about trying to do induction servo applications above 20 horsepower, say a 50 horsepower hoist where we want to do extremely precise positioning, or a gigantic turntable. In these cases, a gigantic turntable, by the way, being an azimuth on a big antenna, that's a turntable. Induction servo is a viable way to do this. It's much more reliable than a permanent magnet motor. It's also less costly. It's going to take up more space, but typically in those applications, you've got more space. So you want to rock the antenna company's world? Propose induction servo versus the expensive permanent magnet servos that you're using. Now, the biggest antennas, frankly, are running around 15 to 25 kilowatts. Divide that by 0.75 and you get your horsepower. And so 15 horsepower is around 15 kilowatts is around 22 horsepower. You're still able to do that with a TENV motor. Now, this construction with brake, blower, encoder, and the motor, as I said, is a bit more difficult to get. We can source those for you. And just give us a call when you need that. Now, I may take the subject up again next week. We're redoing our schedule because I haven't really finished, but I'm going to take an extra 5 minutes. It's 7:58 right now. We're done with this application. I encourage you to download this basic motor and the basic VFD presentations from Yaskawa and review those. I've used this to talk about current control and how we accomplish it with the pulse width modulated waveform. In a future matrix presentation, we'll talk about how matrix more accurately, with less sawtooth and less harmonics, produces the current waveform that we desire in the motor, which is the red line here, the sine wave. But now you understand that blasting a voltage pulse into an induction motor winding creates this current in this sawtooth current pattern in that stator, which in turn induces the magnetic field in the rotor. The disadvantage is that it's not perfectly sinusoidal. So this harmonic, if you will, actually transfers into the magnetic field that we induce into the rotor. So the finer we can make this blue line meet the red line, the better the performance of the motor is concerned in terms of producing current. And then, as we said earlier, once you've got current knocked, it's easy to control voltage in any application that you want to control it in. And when we talk about induction servo applications, position, again, with a feedback encoder. So I hope that, oh, there's one more thing I want to show you, by the way. This is actually how we generate, this is the control waveform that we use, the reference signal in the PWM inverter, pulse width modulated inverter, to generate the on time and off time of the pulses themselves. So here you have the desired sine wave that we're trying to produce, in this case the current waveform. We put this reference signal on top of it in the control board, and it determines the on and off times of the pulses that we send out on that winding. It's actually a very simple algorithm. There's not a lot of magic here. Remember, when we did this in 1983 with, Toshiba, they didn't even, their first drive, what was it called? VT130 G1. It didn't have a processor on the control board. It was not a processor-controlled drive. It had static logic circuitry on the control board. And this waveform was generated to create this rudimentary pulse width modulated output. And it worked quite well. Yaskawa, with their G2 drive, came out in 1984. They had a processor. Why did they put a processor on it? Because they realized, and Toshiba did very closely on with their next drive, they realized that this static reference signal worked in ideal situations. But as the applications changed, whether you're on a conveyor or a fan or a pump or a hoist, you needed to change this reference signal dynamically, reacting to conditions from the field. And that required a processor. So we went to processor-based VFDs in 84 and 85. This reference signal, though, is the basic reference signal that was used on the original VT130G1 non-processor controlled board. Therefore, I use it as an example to show you this really isn't hard technology. It's not difficult to understand. It's a simple pulse width modulated generator. And using the inductive reactance characteristics of the AC induction motor, we're able to manipulate the blue waveform to what amounts to an extremely close approximation of the ideal red waveform, the current we want in the AC induction motor. Thank you for letting me take a little bit of extra time. I hope this was helpful. It's a little bit of a deep dive. If you have any questions on this, I encourage you to drop me an email and I can discuss that with you. I can't emphasize enough how important it is to understand things at this level if you really want to step out and do some applications confidently beyond just running the standard fan and pump and conveyor. It's really what made Yaskawa the powerhouse in the 90s, because we could do these applications when nobody else could. It wasn't necessarily, well, we had a better drive, but we also had good people who understood things, like Jim, who's been a veteran of this field for a long time. Guys like Larry Fuson and, the rest of the guys from the old crew. We had an applications advantage because we understood this core. I'm hoping to give you that advantage in this class. Thank you very much. It's 8:04. Time to go to work. Welcome back from the holiday. And we'll see you next week.
Thank you,
Thanks, Pierce.
Pierce.
Thank you. Bye.
Thanks, Pierce. Appreciate it.